Hello all, welcome to the video lecture series for the subject compiler design. Today I am going to explain you about minimization of DFA. So let me tell you how exactly the DFA can be minimized with the equivalent construction of DFA. Right. So here you can see the definition for DFA, which stands for converting a given DFA to its equivalent DFA with minimum number of states. If the states has been given with maximum, if you are doing down, if you are reducing that into one state, then we can call it as a minimization of DFA. Any given transition table can be minimized with one state, then we can call it as minimization of DFA. This DFA minimization is also called as optimization of DFA and uses partitioning algorithm. So now I'm going to explain you how this algorithm, partitioning algorithm, can be applied to construct a minimum DFA for the following automata. So now you can see the example here. So here they are asking you to construct the minimal DFA for the given automata. So the automata has been given. Now the states has been given. You can see the number of states here is 5 and the input is A and B and the automata has been constructed. Now we are going to construct a state transition diagram for this particular given automata. So let me start. Here you can see the starting state. Here you can see it is A, right? So A is taking an input called A, small a, and it is reaching a destination state is called B. So I hope you can able to follow exactly what this state is projected to. Now again the input is A and A is taking an input A and reaching destination is B. Again you can see A is taking a small b and the destination is C. So for the comfortability I am drawing a C state over here, right? So now A is taking an input called small b and it is reaching a destination state called C. So now the first part is over. So A is a starting state. Now you can see the second part. B is taking small a and it is reaching B. So B is taking a small a and it is reaching B. So it is reaching itself, right? So the next thing is B, a state called B is taking an input small b and it is reaching a destination called D. So for the comfortable part, I am drawing D here. You can construct in your own method and also in your own structure also. So B is taking a small b and it is reaching a destination called D, right? So let me take you to the next state. So you can see the state here is capital C and it is taking a small a and it is reaching B. So you can see here, and the thing C is taking a small a and it is reaching B. So now you can construct in this way, right? So C is taking small a and it is reaching B. Now again C is taking small b and it is reaching C. So it is reaching small b, taking small b and reaching itself. So you can see that, right? So let me take it to the next level. Next state is D. D is taking small a. So you can see here D is taking small a and it is reaching B. So now you have to construct in this way. So D is taking small a and it is reaching B, right? So again D is taking small b and it is reaching E. So we have never constructed a state E, and this state E you can see here it is mentioned in closure asterisk. So that means it is a end state, right? Now where this particular point we have left behind, D is taking a small a, right? D is taking a small a and it is reaching B. So we have been already constructed. And D is taking a small b and it is reaching E. So here it is, right? This is the way you construct. And we have a final part, that is E. So as you all know, E is the end state. So E is taking small a and it is reaching B. So in this way you can construct. So E is taking small a and it is reaching a destination called B, right? So what is the final part here? So E is taking small b and it is reaching C. So C is very near here. You can see here E is taking small b and it is reaching C. So this is the first thing you need to draw a DFA for a given automata. So you can see any state here, we have drawn a DFA. You can cross verify. Any state here is not taking a single input twice from one state to another state, right? So let me take you to the next level here. The level has been already I have taken so that you can able to understand in a frequent way, right? Now the step one here it is, we are going to construct an epsilon closure value. There is no epsilon here, so we are doing only lambda values here. So I'm going to take two different state, right? So before this, so let me draw and explain you this particular transition diagram. So we are going to define two parts here. Number one is pi and number two is pi dash, right? So let me tell you what is this pi. Pi is equal to number of state present here. As you all know, we have A, B, capital C, capital D and E, right? So these are all the number of state. As you all know, which is a starting state here, A is a starting state and ending state is E. So what is this pi dash is, it will separate the end state from the regular state here. So what I am supposed to do, I am going to write pi dash is equal to A, B, C and D. So these are all the states. You can use a lambda value and we are going to see which are all these states are equivalent, which is taking same input to reach the destination, right? So we are going to have the regular states here and write the end state separately. So this is called end state, right? So the end state has to be separated. The pi value is all the states here and pi dash is nothing but taking out the end state and it is separated from the regular state. So this is how it has to be drawn. Now let me take you to the next level. So this is step number one. So we are going to find a lambda values for all the state which is present there. Step number one, lambda of capital A comma small a, right? You can see here. So lambda values we are going to take one by one. You can see here lambda value has been applied for A, B, C, D and E. So that you can able to take this lambda capital A comma small a, lambda of capital A comma small b and find what is the destination state you are getting. So now here you can check it. So I am going to take lambda of capital A comma small a. I am getting the destination called B. You can refer the diagram. And lambda A comma small b, we are getting the destination called C. This is the easiest method, right? And I have taken that for capital A. Now I am going to take that for capital B. Capital B is nothing but the next state, right? So now capital B comma small a, capital B comma small b. This is the next state, right? So lambda of capital B comma small a, that gives the destination called B. You can refer the diagram for this state transition diagram. Lambda of capital B comma small b, that helps you to get the destination, reach the destination called D. So I'm going to check whether this A and this B is equivalent or not. Absolutely, you can check this particular reaching state is different and this particular reaching state is different. So I've mentioned it is not equivalent, right? Again, in the same way, you can take any values as a set and you can compare, right? I have compared initially A and B. Now I am taking into step number 2. Now I am comparing C as well as D, right? So now you can see here same formula, same process. I am doing it again. Lambda of capital C comma small a, it leads to the state called B. And lambda capital C comma small b, and it leads to the destination state called C, right? So I am taking D again. This is the next fourth new state. So here capital D, lambda of capital D comma small a, it takes to capital B as a destination state. And here you can check it, lambda of capital D comma small b, that gets the state called E, right? Now I'm going to check whether C and D is equivalent or not. You can see here this is different destination and here you can see this is different destination. So I have mentioned it is not equivalent, right? So now as you all know that we have defined pi and pi dash. Pi dash in the sense this final state has to be always treated separately. So I have taken capital E comma small a and capital E comma small b. I am not comparing this E because it is a end state, right? So now you can check it, lambda of capital E comma small a, that leads to a destination state called B, and lambda E comma small b, that leads to a destination called C, that is a destination state. Now I am not going to compare this E with any other state. That is the criteria and that is the formula. That is the exact node we need to have it over here, right? So let me take you to the next level. So now here you can see here, take equal states, right? So I am going to take which are all the equal state here. Now you can see capital A is a state and capital C is another state which gives the same output. That is lambda of capital A and lambda of capital A comma B and A. You can check it, we are getting B and C as the output, that is the state. And here also when we apply the same lambda values to C, you are getting the B and C as the output. Now we got it is a equivalent state. So what is the second step? As you all know, we are going to have this pi value here. Pi is equal to, we are going to take this A comma C. This both the states can be treated as A. So that means we are minimizing this a state called capital C as a single state as A. So because the reason is we are getting the same output, same initial states we are getting. So I am going to do in this particular way. B is not equivalent and D is not equivalent. E has to be, whether it is equivalent or not, we are going to treat this E always separately. That is the criteria. We all need to follow this, right? So let me take you to the next part. When you got this, take this lambda value and construct a state transition table. Now see here, wherever you got the C, right? I am going to show this again. Wherever you got the C, that is going to be applied as A, right? So now you can check it wherever I am getting C, right? Now here A an input and another input B, small a and B, I am getting the same thing, right? So here you can check it. A is taking a small b and reaching C. Instead of C here, you can check the original table here. A is taking a small b and reaching a capital C here. But here we are replacing that C into A. So altogether A comma C, we are going to call it as a one single state. So this C has been replaced as A. So you can check it where all this C has been replaced. So next second step, you can see there is no C here. B taking small a to reach B. You can check all the lambda values above and find out, derive this particular thing, right? So I am going for C. C has been already replaced to A. So leave that particular state, right? So we have already minimized it. So go for the other states. What are the other states we have? We have derived B. We are going to derive this D here. D have this small a to reach B and D have this small b to reach E, right? So again go to the last state. Last state is E. So you can check it. E is the end state. So I have mentioned the disclosure value here, that's star. So E is taking small a to reach capital B, and in the previous original transition table you can see E is taking small b to reach C, but here you all know C has been replaced with A, so here it is, right? So this is the final step. I'm going to draw a last state transition diagram that is minimized by using this particular minimized DFA state transition table, right? So what all the steps we have, how many states we have? A, B, C and D. So in whichever the structure which is comfortable for you, you can draw in that way. So I am drawing in this way. You can see A is the starting state and B is the next state and D is the another state and followed by E, right? So now you can see here, now A is taking small a to reach B, so you can able to construct that in the easiest way, right? A is taking a small a to reach B. Again A is taking small b to reach A, so A is taking small b to reach A. Go to the next level. B is taking small a to reach B. So here it is. And B is taking small b to reach D. So here it is. Right. So go to the next step. D is taking small a. D is taking small a. See the table and do. D is taking small a to reach B. So D is taking small a to reach B. Again, D is taking small b to reach E. So D is taking small b to reach E, the small b. And finally, we have an end state. Don't forget to mention the structure of the end state. So E is, that is final state. E is taking small a to reach B. Here it is. So E is taking a small a to reach B. And E is taking small b to reach A. So E is taking small a to reach, small b to reach A. So you can see, initially we have a diagram here. So you can check the diagram here. We have constructed the same automata in 5 different states. All these 5 different states has been reduced into 4 different states. So this is called as the final state. Draw a state transition table for the above diagram. We have derived this particular state transition table and the final output will be this. Thank you.